Yep. Yeah, I think we should start. Yeah. Our next speaker is Yuya Tanizaki. He will be talking about topology of SU and over Z and lattice gauge fields. and generalized Hooft anomaly.
Yeah, thank you for introduction. And I really thank the organizer having this workshop. Yeah, I really learned a lot of things, so yeah, I enjoy a lot. And also having, I'd like to thank for giving me this opportunity to talk about my recent work. So talk is about some topology of lattice gauge field and its relation to recently discovered anomaly. And it is based on this work in collaboration with Hiroshi Suzuki in Kyushu University and his student Motokazu Abe, Soma Onoda, and a postdoc at Osaka University, Okuto Morikawa. So this is a conference about confinement, so I don't have to say much about this introduction. But the talk is about 4D and YAML theory, and it's a very interesting theory. It's a fundamental theory of strong interaction, generates an exponentially small mass gap, so having a mass gap out of basically nothing. And also this shows the confinement of quarks. So if we put the color degree of freedom, they are confined with electric strings. And these are basic interesting property of SU YAML theory, but recent days we have uncovered that so confining vacuum of YAML theory have more rich structure than we have expected. So to talk about it, so let's add this kind of topological term to the SUN YAML gauge field. So in continuum field, as a continuum field theory, SUN gauge field has a non-trivial topology because of this discretized topological quantity. And this allows us to introduce the theta angle to the YAML theory. And the path integral is given by this kind of thing with YAML kinetic term in, and you can add this theta angle term. And in this sense, so YAML vacuum has a continuous parameter called the theta angle. And because of this quantization property of topological charge, so theta is a 2π periodic variable or 2π periodic coupling constant. So it deserves the name of calling it as an angle. And this theta angle has this kind of 2π periodicity, showing that so partition function with theta has and partition function at theta equal 2π are basically the same. And this tells us that so YAML theory at theta and theta equal 2π are unitary equivalent. So, but this is not the end of the story. So this YAML theory has a symmetry called the center symmetry, or recently it's more sophisticatedly called as the N1 form symmetry. And regarding it as that kind of sophisticated version of the center symmetry, and we can couple the background gauge field so for the center symmetry, and you can study the partition function, including the background gauge field here. And here, 2π periodicity of the theta angle is lost. So if we compare the partition function at theta and theta equal 2π, there is an extra contact term that depends on the background gauge field for this to achieve this equality. So although YAML's theory at theta equals and theta equal 2π are unitary equivalent, but vacuum at theta and theta equal 2π are distinct as symmetry protected topological phase with center symmetry. This relation is found by these gentlemen, so Zohar and his collaborators. And Eric talks about its outcome as a semi-classical realization as a first talk in this day. And we have seen that, so for example, at theta equal pi, we have twofold degeneracy at the non-perturbative level for the YAML's vacuum. And this is found already about 6 years ago. So this relation is 6 years old. And I think many of the participants here are benefited from have a great benefit from this kind of exact relation of the YAML's partition function. And we can study, we can uncover many things on YAML's confining vacuum, just having this rigorous relation for the YAML's partition function. But let's stop a bit. So this key relation is derived from analyzing the smooth and classical gauge field. So basically, this derivation comes from the fact that so YAML's topological charge with Hooft twisted boundary condition has 1 over n shift. So topological charge is shifted by the fractional value under the presence of Hooft twisted background, Hooft twisted boundary condition. And that 1 over n shift of the topological charge affects this counter term for comparing the YAML's partition function at theta equal 2π. So this relation is basically was derived from that observation. But then here we have a natural question. Does this important relation hold at the renormalized and non-perturbatively quantized Yang-Mills theory? So this is a question I'd like to answer here. And the answer is yes, it does. It does hold as a rigorous relation for the quantum Yang-Mills theory. And what we will do here is so we will extend the work of Martin Lucia in 1982. So in that time, so Martin derives or introduces the notion of topology in lattice gauge field. And we extend this work for SU and gauge field, now coupled with background gauge field for center symmetry. And we define a nice topological charge that is local in lattice sense. And this topological charge is physical in the sense that it is SUN and center GN1 from gauge invariant. And this topological charge has an expected quantization property. So this topological charge is basically quantized integer, but under the presence of V field, it is shifted by 1 over n. That is completely characterized by the background gauge field for center symmetry. And as a corollary of this useful property of Yang-Mills lattice topological charge, we will show that this relation holds at the lattice Yang-Mills theory at finite lattice spacing. So this kind of relation could not be spoiled by lattice gauging, lattice regularization for Yang-Mills theory. So basically, this is a punchline of my talk. And from now on, I'm talking about how we derive or how we define this nice topological charge on the lattice. Okay, so before that, so before going to our work, let me tell a brief idea of what Lucia did in 1982. So in continuum field theory, so that this topological charge is classifies a homotopy class of SUN gauge field on continuous space-time. And this is roughly a total derivative quantity. And that suggests that so this topological charge depends only on the transition function or boundary condition of the gauge field. And the question is, how do we derive that kind of twisted boundary condition for SUN gauge field out of this lattice setup? So in this lattice setup, so SUN variables are living on the link. And basically, this is the whole quantity to define the SUN lattice regularization. But in continuum, what we want is, so we have patches, and there are many patches to cover the whole space-time. And there is an overlap. And one whole gauge field are living on this patch. And on this overlap of two patches, we want to connect the description of two gauge field, and we need a transition function that connects the gauge field on one patch and the another patch by this gauge transformation function. And in this kind of overlap, there are several ways to connect gauge field here and gauge field here. And that requires that this SUN transition function has to satisfy this kind of cocycle condition. And having this nice transition function, you can compute the topological charge. And the question is, how do we obtain the data of this transition function out of this lattice data? And what Lucia did is, so this kind of nice topological charge, nice transition function can be obtained out of this SUN link variable if it satisfies what is called as admissibility condition. I will go back to this, what it means later, but so basically this is what Lucia did. And what I will do from now is to extend this work to the case of SU and Yang-Mills theory coupled to background GN gauge field, background center gauge field. So our setup is we consider SUN link variable living on this kind of link. And in order to introduce a background gauge field for the center symmetry, we also introduce this Zn valued bracket variable that is living on this bracket. And our Wilson gauge action can be given by this. So out of this SUN bracket variable, by multiplying its SUN link variable and multiplying it in this way, we define the SUN value bracket. This is roughly saying that this is the exponentiated version of the SUN field strength. And we basically take a trace to define the field strength square as a Wilson action. But in addition to this, under the presence of this Zn valued bracket variable, bracket gauge field, we attach this Zn phase in this way. And here, so I will assume that this Zn valued bracket variable does not have any local dynamics. So I'm assuming that its field strength is 0. So basically, I'm saying that this Zn valued field is flat or does not have any lattice monopole here. And a notable property of this Wilson action coupled to this Gn background gauge field is that so this is invariant, of course, invariant under SUN gauge transformation. And also this is invariant under what is called as Zn valued Zn one form gauge transformation. That acts on this background gauge field as shifted by the total derivative of Zn valued total derivative of Zn valued one form field. And on the link variable, so this Zn valued transformation acts really as a center transformation. So this manifests the fact that so this background gauge field is really the gauge field coupling to the center transformation. Okay, so here let me talk about what about admissibility condition. So this link variable, the space of this SUN link variable is just a space given by SUN to the number of links. So basically, this is a connected space. So that means that any configuration, so any lattice configuration can be continuously deformed to the trivial configuration. So unlike the case of continuum SUN gauge field, any configuration are continuously connected. So of course, without importing any condition, that means that we have no notion of the topological differences for any lattice configuration. So unlike continuum case, in this sense, lattice gauge field has no topological sectors. But this is not the whole story, and this is what Martin Lucia pointed out in 1982. So in order to study the confinement and reproduce the continuum limit, what we want to achieve is the weak coupling limit. Then we generate the exponentially small mass gap. Then looking at this action, and this beta is basically 1 over g squared, that roughly says that so this bracket variable should be sufficiently close to the identity. So dominant configuration of the path integral should be restricted to these very, very tiny regions. And that means that, so, okay, then let's try to restrict your configuration of the path integral in this small region, while now, unlike here, so we just take some order 1 number, which is just roughly 0.1. It just needs to be smaller than some pi or something, but it can be taken to be independent from coupling constant, lattice spacing, lattice sizes at all. And if this lattice field strength is smaller than this some small order 1, smaller than this order 1 number quantity, then let's call this gauge field as admissible. And what we will do is instead of performing the path integral over whole region of the SUN link variable, let's restrict the path integral into this region. And since this region covers this dominant configuration, it would not affect the continuum limit at all. So this is just an irrelevant deformation of the lattice Yamu theory, at least in the continuum limit. And just having this admissible condition, it will turn out that we can now introduce a topological now we can introduce a notion of the topological sector by having this admissible condition. Yeah. And now, so I will impose this condition from in the talk in the following of my talk. And from now, so I'm now trying to construct the transition function out of the data of SUN link variable. And I try to draw a nice figure, but it turns out to be complicated. So instead of showing this, I think lively drawing the same figure here would be more convenient. So I will do that. But before that, so let's introduce the notion of the complete axial gauge. So in order to define the patches and transition function, we have to fix the gauge so that we can reproduce the notion of continuum gauge field out of the lattice. So this kind of link variable can have order 1 fluctuation. So basically, so this kind of link variable does not have a good notion about its close to. So without having any gauge fixing, this U can be arbitrary, so it's not close to 1. So gauge field for this link variable does not have a good continuum notion. So what we do is for each point, we take the complete axial gauge. So drawing this kind of lattice. Yeah. And let's call that this point is N. And let's draw that. So let's draw a tree so that it does not have any closed loop, something like this. And what we do is, so if we introduce a notion of complete axial gauge for this site N, and that is described by this subscript. And for example, let's take a link variable connecting AB in this context. And what it did is, so first what we do is connect starting from N, go to A, and consider the link variable AB, and from B along this red path just coming back. And in this case, so this is just 1. So if you take the points A and B within this tree, so this link variable is just 1. And in this sense, this is called a complete axial gauge. But if we take another AB, which does not belong to this red curve, for example, something like this, A and B, then in this case, what we will do is first we want to connect N and A along this red path. So I forgot to wait. Yeah, so this should not be red and this should be red. So first go from N to A, so like this. Then connect A and B as the link variable and coming back. So in this case, UNAB is a bracket given by this one. So point is, so in this complete axial gauge, any link variable is always a loop starting from N and connecting A and B and coming back. And under the presence of admissibility condition, this is always close to 1 plus order epsilon. That means that so gauge field in this axial gauge is always small, sufficiently small enough. Yep. Okay, so. Exactly. So in this case, I don't think, wait. In this case, I don't think so. Or maybe it is there is a gauge transformation at N can act as a global transformation, but here, so here we just multiply just a link variable along this path, so there is no ambiguity in this construction here at least. Yeah. So in this way, so we introduce a bracket, a complete axial gauge. And since this is always a loop, so under the one form transformation, so if we attach sufficient number of Zn valued bracket variable, for example, filling here, then this kind of complete axial gauge link variable can be made completely one form gauge invariant. And now, so here in this, now we define the completely axial gauge at each site. And now we want to define the transition function. So what we want to do is, so if we have 2 patches, and in this overlap, we would like to define the transition function. So, and the way to do it is, for example, let's call this is A and B. And let's consider that so this link variable now have 2 representations. So it can be represented by complete axial gauge starting from this side, A and B. But it should be gauge equivalent to another completely axial gauge starting from this site N. And so this should be gauge equivalent. That means that so this should be equal by some gauge transformation B tilde B inverse, and yeah and mu and mu. Yeah. And in order to do it, so we should compare two paths. So UNAB is just this cycle, just this loop, and UN minus mu AB is wait, it's something like this. And in order to, and these two are of course not equal, but if you multiply the transition function, something like going this way and then coming back, then these two paths are cancelled out. And this part corresponds to this transition function for the first one at site A. And in order to obtain this path, we just need to attach this one. And this corresponds to Bn minus mu at site B. So since UNAB and UN minus mu A hat AB gives a completely axial gauge in different parties, so this gives a nice notion of the transition function here at the side at the corner of this overlap region. And this transition function turns out to satisfy a nice property having this kind of cocycle condition at the corner. But the point is, so here transition function is still defined only at the corner, and all the construction for here doesn't care about the admissibility condition. But what we actually want to do is to define the transition function over the whole overlap. So transition function at the corner is of course insufficient information. So we have to interpret this transition function into the whole overlap region. And this formula is actually so complicated, but so using the data of transition function at the corner, you can interpret that transition function to the whole region of the overlap by having this kind of interpolating function without violating this cocycle condition at all. And the formula of this interpolating function is very complicated, and I do not have a good intuition under it. So please ask Martin Lucia for the intuition behind it. But if you believe this formula and use the admissibility condition, then this interpolating function has a very nice property, and this cocycle condition turns out to be true for all the region inside this, for all the overlap region. So in the case of, so under the presence of B field, basically all this link variable has to be constructed in the one form gauge invariant way. And but if we impose manifest one form gauge invariance at the same state at the every stage, then Martin's construction turns out to be nicely extended to this setup. Yeah. So admissibility condition. So here, so this y is a coordinate for this cube that is a continuous variable within 0 and 1. And in order to define this interpolation, you have to take this fractional power for unitary matrix. So that is basically saying that you have to perform the inverse log transformation from exponentiated unitary matrix to traceless Hermitian matrix. But for that inverse transformation, some kind of the admissibility condition is necessary, or it should be sufficient close to the identity region to perform this, to take this fractional power. So in this interpolation, admissibility condition plays a key role. Okay, then so everything what we have done is, so out of this lattice data, we now construct the nice transition function that defines the continuous SUN over GN principal bundle. And now using this transition function, so you can compute this kind of local topological charge. And this now defines the total lattice topological charge out of lattice data. And since in the construction of this transition function, we only need the information in the adjacent cells. So our construction is completely local. And it turns out that every step is manifestly SUN gauge covariant and GN1 form invariant. So this construction gives gauge invariant lattice topological charge. And now, so with using the data of the cocycle condition, just open Van Baar's paper, and then it turns out that so this topological charge has integer quantization with this 1 over n fraction shift. And that fractional shift of the topological charge is completely controlled by background gauge field. Yep. Yeah, so here, so if we in order to get this fractional part, so there is an ambiguity for the lifting to the integer. So this B is just GN gauge field, but and in order to get this kind of expression, we need to take the integer lift to integer valued cochain. And in order to be completely invariant under that choice, this couple one product is important. Yeah, but yeah. Yeah. That does not. So this decomposition is not invariant under that lift. Yeah. But in modulo 1, this is a well-defined one. Yeah. So under the change of the lift, these two are exchanged a little bit. Yeah. Modulo 1. Yeah. Modulo 1. Yeah. And having this relation, now we can obtain this relation as a Yamu's as a lattice Yamu's partition function at finite lattice space. Okay, let me summarize. So what we have done is so following Lucia out of SUN gauge field coupled to GN background gauge field with admissibility condition, we now define the well-defined local and gauge invariant topological charge. And our construction is basically the extension of Lucia by coupling the GN background gauge field. And by making the manifest one form gauge invariance at the every stage of his construction, all the proof turns out to be extended nicely. And the take-home message is now this relation is derived as a lattice regularized partition function of the Yamu theory. So even if you are a hardcore latticean who are not so much care about continuum, now this is your tool too. Okay, and possible future direction is so here we extended Lucia's geometric construction of the topological charge under the presence of this GN2 form background gauge field. But that geometric lattice definition does not necessarily have a close connection with index theorem of overlap fermion. Or at least what I mean is not at the current stage, a connection between index of overlap fermion and this geometric topological charge is not known. So in order to extend this study or this anomaly to the lattice adjoint QCD, chiral anomaly of lattice adjoint QCD, we need further investigation on lattice topology of gauge field. So this would be a good future work for us. Okay, that's basically everything. Thank you very much for your attention. Yep.
Questions?
But practically speaking, so having admissibility condition, so basically acceptance rate of Monte Carlo step could be delayed. So yeah, so you have to pay some cost for yeah.
They usually simulate normal, but they cool if they're gonna use it.
Right, but precisely speaking, so under that gradient flow step, so maybe topological sector could be ambiguous or something. So as long as if we only pick up admissible configuration, and if gradient flow step keeps that admissibility condition intact, then that topological sector should be always the same. But yeah, in general, it's not so clear. Yeah.
transmissibility condition. I mean, if all you wanted to do was keep your link variables small, then something like lattice Landau gauge would do the same thing.
But so here point is, so this kind of admissibility condition is gauge invariant condition because this is the bracket. So under the gauge transformation, so same unitary matrix appears on left and right side.
All you need is decouple to satisfy that.
Yeah, but so here, so I want to make every step manifestly gauge invariant. So within this formalism, we do not perform any gauge fixing. Yeah.
This the field is like external field. I mean, it's not dynamical or
Yeah, so here it is treated as non-dynamical. Yeah, non-dynamical. But yeah, but you can sum up this B field with satisfying this constraint, then you can define a PSU and gauge field.
what's this construction or
No. Here we just pick up a specific configuration of B field satisfying this constraint. Yeah.
yeah, no, because you also put dynamical part as well, right?
So yeah, so this SUN part is completely dynamical. Yeah.
When you're constructing theta should be by 2 pi, what about as quantum of theta? You also can construct for any theta.
So what we have defined is this topological charge. So yeah. So we can now define this topological charge with background B as a path integral of this link variable, but it's now restricted to this admissible configuration. And just consider S Wilson plus I theta Q topological, and this Q topological is that Q topological. Yeah. So now Yamil theory at any theta is defined in this way on a lattice. Yeah. Exactly, right. Yeah, right. Exactly. Right. Yeah, so for example, you can perform gradient flow. So if gradient flow is now done with this Wilson action coupled with B field, then gradient flow gives a good continuum configuration under the presence of B field. And indeed, so if that kind of classical approximation works well, then this Q top is really F tilde, where this F and F tilde is given by this exponential phase of this U tilde bracket variable. Yeah. So if in the naive classical continuum limit, this topological charge is same with FF tilde. So if you have a nice gradient flow to achieve that nice classical configuration out of lattice field, then you can compute it in a naive way. Yeah. Here, no. Yeah, but for example, having a boundary, so change of the topological sector is more easily done. So for example, yeah, as a process of the Monte Carlo hybrid Monte Carlo update, it's possible that we can take open boundary and just making closed boundary, closing the boundary and sampling it. So that gives makes the barrier of topological sector much less. Yeah. I'm interested in, but currently I have no idea about.
The singular. He constructed also a definition of from a term silence parent
I see. Yes. Right, right. So under the gradient flow smearing process, it should be ensures that this kind of admissibility condition should not be violated. Yeah. But the point is, as long as gradient flow is keeps this admissibility condition is intact, topological charge does not change. So if gradient flow violates this condition at some stage, then topological charge becomes ambiguous. Yeah. So if you perform smearing too much, then at some step this condition should be violated. Yeah. So you have to be careful that this condition should not be violated at any smearing step.
I didn't understand it. You already said that direction, but you could also try to define the topological charge by
Overlap fermion, right.
I mean, this is what I meant.
Yeah, right. And the index, right. That's
So
exactly. But even in fundamental case, so overlap definition of topological charge and this geometric definition of topology, so connection between them is not yet so clear at finite right spacing. Yeah. And indeed, it's one of the important program of constructing chiral gauge theory. Yeah, we have to know much data about the local cohomology of lattice gauge field to construct chiral gauge theory. Yeah, and that is one of the big problem inside it. Yeah. Yeah, thank you so much.